Okay, guys, so as promised, I'm going to do a video lecture today in lieu of a live or synchronous lecture since Nick did the review session and administered the quiz today. I really hope that that worked for everyone. I will be asking for your feedback tomorrow in class, and we'll see how it went. I instructed Nick to do examples that were very close to what you would have seen on the quiz. So if you're paying close attention and following the solutions that he was writing during the review session, then the quiz should have been a cinch. But I can appreciate the fact that the stuff is hard and there's lots of details, right? The devil's in the details. So I'm doing my best to make this class as accessible and achievable as I can, right? You may have noticed that the second test, the one that you just took on Friday, every single problem was exactly identical to the ones that I did in the review session on Thursday, which I posted solutions to on Thursday. So if you looked over that, if you studied it, if you followed it, then yet again, the test should have been a home run. I will hopefully be getting those graded and back to you by Friday. So stay tuned for that, right? But we've got to pick up where we left off, which was with series, right? We had just finished talking about telescoping series, and now we're going to pick up downstream of that, right? So just making sure that I'm recording. It appears that I'm recording. So let's get going here. So we stopped talking about telescoping series, and today I'm writing down a very important theorem. This theorem is really useful for determining whether a series doesn't converge, but not necessarily whether it does converge, right? So what's the theorem in question? I hope everyone can see this easily enough. The theorem says if we have a series that is convergent, then that implies that the corresponding sequence of values, an, must go to 0. Okay, and the idea behind this theorem is that if I'm adding something up infinitely many terms of something and that thing doesn't eventually converge to 0, then I'm always adding something positive with actual extent, and that's going to cause the sum to diverge, right? So we need the thing that we're summing over to converge to 0. This is really useful, like I said, for determining whether a series doesn't converge, but not so useful for determining that it does. So let's look at an example. So example 1, we're just looking at the sum of n squared. It's always assumed when I write this that we are summing over infinity, but if you want to see it, you can just say 0 to infinity or 1 to infinity. It doesn't matter in this case. So our expectation is this thing definitely is divergent, right? I'm summing squares of a number, so this thing should blow up, and indeed it does. But how do I prove that? Well, in this case, I can use the theorem here to show that this thing doesn't converge, right? So what would I say? I'd say, hey, look, n squared as a sequence, this thing goes to infinity, right? For every n that I plug into it, it just gets bigger and bigger and bigger until it diverges to infinity. So that implies that this sum does not converge. Okay. So we can use the idea that the sequence doesn't go to zero to show that the series doesn't converge, but it doesn't always follow in the other direction. So another example. Suppose we're looking at the series of n plus 1 over n, right? So does it converge or does it diverge? Yet again, we can look at the sequence, n plus 1 over n. And if we're looking at the limit as n goes to infinity, then this thing will go to 1. So it's the ratio of the leading coefficients. 1 is definitely not 0. So yet again, that means that the series diverges. In particular, it's going to diverge to infinity. Eventually, we're just adding 1 over and over and over again. 1 plus 1 plus 1 plus 1 infinitely many times is definitely going to go off to positive infinity. Okay, so useful for showing things don't converge, or say, in other words, useful for showing things diverge, but not always useful for showing things converge. So the paradigmatic example is the harmonic series. So we're summing 1 over n. And remember that by analogy, we can think of this as an integral of 1 over x dx. And we learned way back in 8.7 about all the integrals where we were considering the values of p power of x in the denominator. And in particular, when p equals 1, we found out that this thing diverges. So this is the continuous version of the discrete harmonic series. So we should expect that if I look at the continuous version and it diverges, then the discrete or finite version definitely diverges as well, right? So this is what we call a harmonic series, and you can take it as gospel that harmonic series diverge. But, and this is a big but, notice that 1 over n, the sequence, goes to 0. So the sequence goes to 0, but the series diverges. So this is showing you how this theorem isn't useful in all cases, right? It's mainly useful for showing things diverge. It does not show things converge. Because had I made the argument, hey, look, the sequence goes to 0, therefore the series must converge, I would have been wrong. So the logic doesn't follow, okay? So that's a very important caveat to using this theorem, but this theorem is ultra useful. It's one that I reach for quite often. This is the first step. When you're looking at a series, you should always check the sequence goes to 0. If it doesn't, then you know you're not, then you know it diverges and you're done. All right. Just going to pause the video real quick. I just wanted to check to see that this was all legible from the phone screen. And there is a bit of a glare right here, which I hope doesn't cause any issues, but it looks like everything is readable. So I'm going to keep going with this. All right, so very useful theorem indeed. So this is starting to become predictable, but we always have a theorem in all of these sections where we're talking about the properties of whatever critter we're interested in. So whether it was improper integrals or sequences, and now in this case series. So this is properties of series. These are infinite series. Everything is infinite series in this case. So what can we say about general series? So if we have a series AN that goes to A, converges to A, and actually I'm not going to use the equal sign because that's a little bit of an abusive notation. So I mean, you can use it, but I like keep making sure that you know that we're talking about a limit here. And we have another series that converges to B, so they're both convergent. Then what can we say? We can say the sum or difference of the two sequences, when we sum over them, this will converge to the sum or difference of their respective limits. And we also always have the constant term. So if we multiply a AN by K, where AN is the sequence, and then we sum over all those, basically we can factor out the K, and this will then go to K times A. So just things that we can reach for when we are working through series. We have these truths that we can invoke, and perhaps they'll be useful. Now there is a corollary, which is a fancy term for sort of a result that follows from what we see here. And that says that if, let's see what's here. If our series is divergent, then that implies that the sum of K times AN is also divergent. And then this one's a bit trickier. If I have one convergent series, so let's say AN converges to A, and I have a divergent series, BN. So divergent, remember, could mean goes to infinity. It could just mean it never settles on one number. Think of like a ping pong situation, like an alternating sequence, like we saw last time. But the main idea here is I've got one converging series and one diverging series. Then the sum or difference of these two series is divergent. So basically, BN is a rotten apple. It spoils the whole bunch. If we have one divergence series, then it's going to ruin the convergence of the other series. But this is a really important point, because you have to have only one divergent series. You can sum two divergent series and end up with a convergent series. Or you could, you can go, so if they were both divergent, then we could end up with something that was convergent. But when only one of them is divergent and one is convergent, then the sum or difference of the two is divergent. So consider the example, just to show that we have to be careful here. If we have two divergent series, so let's define our AN to be 1 plus 1 plus 1 off to infinity. And similarly, we define BN to be -1, -1, -1, so on. then these are both divergent series, right? The sequence doesn't go to 0. AN is just 1. BN is just -1, right? Not the series, just the sequences. So by that theorem that we saw earlier, these things are definitely divergent. But if I add the two, AN plus BN equals 0, right? 1 minus 1, all the ones and minus ones cancel. And so we end up with a convergent series defined by the sum of two divergent series. So that's that's sort of a word to the wise. That just because two divergent things, you have two divergent series, doesn't mean you're going to get a divergent sum or difference. Okay. Cool. So this is the majority of the material that we needed to cover about series. The rest of this session, I'm just going to do example problems. I think it's really important that you see how to solve these things, how to think. I want to model solutions for you, just to be more helpful. I'm totally sympathetic to the fact that this class is just coming at you like a fire hose, right? It's just a ton of information. And I'm doing my best to try to slow it down, but I do have to keep up with Mrs. Sherman's curriculum, or what she's defined the course to be, which means that we have to keep up the pace, and I'm already falling behind. So let's do some example problems. So these are just coming straight from the book, in no particular order. So how about we look at 53, odd number problem. Here we're asked to look at the sum from n equals 0 to infinity of 1 over the square root of 2 to the nth power. So this is how these will go. You'll be given a series, and basically the main goal is to determine whether it converges or diverges. In some cases, it'll converge in a way that you know what the convergent value is, what the limit is. Not always the case. In this case, we have a geometric series. So that means we know what it converges to. And we know that it converges, period, right? So R, which is the ratio here, the absolute value of R is the absolute value of 1 over square root of 2. And that is definitely less than 1. So that implies that this is a convergent geometric series. And in particular, we know what it converges to. So this guy we know is going to converge to, remember we have A over 1 minus R. So for us, our A is 1 and our R is 1 over root 2. So this is going to converge to 1 over 1 minus 1 over root 2. And of course, we can clean this up, find a common denominator in the bottom, and at least write it as root 2 over root 2 minus 1. And I don't really care about rationalization or anything like that, but we can clean this up a little bit if we so choose. So that is our solution. It's a convergent geometric series, and even better, we know what it converges to. So that's really cool. All right. Let's look at another one. So this is number 55 from the back of the book. I'll give you you can keep track of the numbers if you care. 55 in the back of the book, we're looking at the series n equals 1 to infinity, -1 to the n plus 1 times 3 over 2 to the n. Right, so we're handed this guy, and your first instinct should be, this looks like it's probably a geometric series, but we need to get it into the right form. We need to make it look right. Now remember, I made a big point about how we can start our geometric series either at 1 or at 0. But if we start it at 1, then we need to have n minus 1s. And if we start it at 0, then we need to have just n's. So we can do one or the other. We just have to figure out how to write it that way. So in this case, I'm going to try to make all the exponents into n minus 1s. That way I don't have to change the index here in the series. I just need to change the powers here. So how do I do that? Well, what I'm going to do, and this is a technique that will you'll use in ordinary differential equations, and even I think later in this class, we're going to break off some of the terms. So what I mean is, I'm going to take out 2 of the -1s from that, and if I do that, then this -1 becomes n minus 1. So I added n plus 1, and I'm taking 2 of the -1s out. I'm factoring it, factoring the -1s out. And so that will bring me to an n minus 1 on the -1. And remember, my goal is to get n minus 1s on both of the powers. There's still a 3 here. And we're going to use the same argument with the 2 here. I want an n minus 1 on the 2, so I'm going to break off one of the 2's. So take some time, squint at this, and convince yourself that if I multiplied this back out, I'd end up with 2 to the n. And likewise, if I multiplied -1 squared times -1 to the n minus 1, I would end up with -1 to the n plus 1. So once you're convinced of that, then we can rewrite this whole thing. I'm going to pull out the terms that I just broke off, because they don't need to be there. Or actually, no, we'll leave them in the front, because that's how these geometric series are defined. But what effectively is going to happen is everything here and the 3, that will all become the A. The A that we're used to seeing with the geometric series. And what's left will become the ratio. So if I multiply this all out, I have -1 squared, which is just +1, and I'll have a 3 over 2. So that's my A. And then my radius to the n minus 1 power will be -1 over 2 to the n minus 1. So all I've done is rewritten the series so that it looks like a geometric series. I need to make sure that if I have an index starting at 1, that my power is n minus 1. I could have also made it so it started at 0 and I had an index a power of n. It's really your choice, but you have to make sure it's right. So once I have it in that form, then it looks like a geometric series. The ratio, the absolute value of the ratio is less than 1, so it definitely converges, and we know what it converges to. A over 1 minus r. R is negative, so it's going to be 1 plus r in the bottom. And if you do some cleanup on that, you'll find out that that actually just equals 1, right? 1 plus 1/2 is 3/2. 3/2 divided by 3/2 is 1. So this is a really important technique to master, how to move pieces around inside the summand. That's what this is called, right? We have an integrand when it's an integral, but when it's a discrete sum, we call that the summand. How do we manipulate the summand so that it looks like a geometric series, so that the index and the power have the right relationship? A very important skill. Okay. Pause real quick. Okay, I wanted to stop and check on that glare. It was pretty bad. I could see that it made some of the stuff illegible or hard to read. Hopefully the previous lecture wasn't too impaired by that. I don't have any way to monitor it. So rather awkwardly, I am going to lecture in a dark room, but I think that makes this legible. And in fact, I got a shade over here. Let me see if I can change that. Okay, I tried pulling the shade, but it brought some more glare back in. So I think you can still see it even though I'm in a dark room. There's no glare, so that's better. A little goofy, but this was a bit of an experiment to see whether doing this on the board versus doing it on paper, what worked better. You guys can give me feedback tomorrow on what you prefer. I kind of like writing at a board, but I understand if the visibility issue is less than ideal. Right. Okay, so let's look at another example. This is number 57. And this, we're looking at the sum n equals 0 to infinity of cosine n pi over 2. Right, so yet again, our goal is to determine convergence or divergence. If it's convergent, can we figure out what it converges to? Maybe, maybe not. Basically, the only one that we know as of now is the geometric series. It's the only one whose convergence or limit we actually know or we can compute. So if it's not a geometric, then all we can say for sure is it's convergent or divergent. So what do we say about this guy? Right, so sometimes it's useful, well, it's definitely always useful to take a look at the sequence first, right? And this goes back to that theorem that we talked about today. If there's something weird with the sequence that we're summing over, then the series will be divergent, right? And so we always want to look at that first. So suppose we look at, I can give it a name. This is an equals the cosine of n pi over 2. What does this sequence do, right? In other words, does it go to 0? Because if it goes to 0 as n goes to infinity, then we at least know that we have it could possibly converge. We don't know that it converges, but we definitely know it doesn't diverge. So what does this thing do? In this case, it might be useful to look at terms in the sequence. So when n equals 1, or we start at 0 actually. So when n equals 0, we have a0, which is cosine of 0 pi over 2, and that's the cosine of 0, which is just positive 1. So a0 is 1. Look at the next term. What does it look like? So when n equals 1, we have the cosine of pi over 2, right? N is equal to 1. What is the cosine of pi over 2? It is 0. All right, keep going. N equals 2. What is this? The third term in the sequence. Now we'll have cosine of pi when we plug in 2. and cosine of pi is -1. And so if we keep doing this, we're going to see a pattern, right? We're going to bounce between 0, +1, 0, -1. And so ultimately, cosine of n pi over 2 basically is an alternating sequence. So we can see that cosine of n pi over 2 is, roughly speaking, -1 to the n. We don't have to be precise about this. This isn't exactly true, but it's definitely alternating. And therefore, right, that implies that an, cosine of n pi over 2, is divergent. It doesn't go to 1 or to 0. In other words, it does not go to 0. And so therefore, by that awesome theorem, this implies that the series diverges. You can see how useful that theorem is. Useful in particular at determining that a sequence diverges, not useful for determining whether a sequence converges, only that it diverges. So, but it should be always the first thing we check. Look at the sequence. Does that sequence go to 0? If it does, then the series could converge or it could diverge. If the sequence does not go to 0, then it definitely diverges. The series does. And your head's probably swimming at this point because I'm saying sequence, series, sequence, and you got to keep that straight, and you really do. You have to get this tattooed on your brain. This has to be fixed in the tissues of your brain, that a sequence is just a list of numbers in a particular order, and a series is the sum of those numbers, right? So we're often moving between the two in order to say something about one or the other. And sequences generally are easier to work with than series. Weird things can happen when you're summing up over infinitely many terms. Sequences behave a little bit more intuitively. So if we can reach for a sequence to say something about a series, it can often give us a better foothold. All right. Let me check the time real quick. Right. I think we have time for at least a couple more examples before I close out the lecture. So let's look at some more. So this is number 59 from the book, in case you want to look it up. We're looking at the sum from n equals 0 to infinity of e to the -2n. So as I stated for this quiz you just took today, I really like examples that have transcendental functions. So exponentials, logarithms, trig functions, inverse trig functions. I often find them more interesting, but often trickier too. So here we have an exponential, what to do with it. Obviously, we want to figure out whether this converges or diverges, and maybe even what it converges to if it is convergent. So how to look at this thing? Well, once you see enough of these, you'll start getting a feel for it. But this is actually a geometric series in disguise. So yet again, we have to do some work. We have to massage the summand to make it look like a geometric series. And how do I do that? Well, e to the -2n, I can rewrite as 1 over e to the +2n. And that, in turn, I can write as 1 over e squared to the n. So take a second, squint at that, and convince yourself that this is true, that we started with e to the negative 2n, and we can rewrite that as 1 over e squared to the nth power. And our index for our sum is starting at 0. So if this is a geometric series, we have the right relationship between the index here and the power. So the only thing we have to determine is whether our ratio is less than 1, whether the absolute value of the ratio. So absolute value of the ratio is the absolute value of 1 over e squared. Is that less than 1? Well, e is 2 and some change. So if I square something, I square e, it's going to be at least 4, which means this is definitely smaller than a quarter, which means it's definitely smaller than 1. So that implies that this is a convergent geometric series. And so we know what it converges to. So it converges to 1 over 1 minus 1 over e squared, right? That's our a over 1 minus r. And we can clean that up just a little bit, just to make it look a little tidier. And that's e squared over e squared minus 1. So a really nice little problem. Totally, this is test and quiz worthy. Such a simple, quick write-up. You have to understand the properties of geometric series. You have to make sure you have the right relationship between the index and the power. You have to make sure that the ratio is less than 1, and then you can write down the actual convergence value. So a nice example, a quick write-up for a solution. So I dig it. All right, I think we can squeeze in one more for good measure. I apologize for the dark room situation, but I think that it removes the glare from the board, and I think that's probably more important than you being able to make out my facial features with any precision. And it might look great. I can't see the screen while I'm working, so I'll know once I upload the video, and you guys can give me feedback. All right. Anyways, last example before we wrap up. You can see a lot of these examples end up being geometric series. The reason why is that you can actually write down what they converge to. So what are we looking at? Sum from n equals 0 to infinity of 2 to the n minus 1 over 3 to the n. This one looks a little weird, right? Because it doesn't look like a geometric series at all. I mean, it's close, but there's something, it's messy. I can't, what I want to do is be able to pull, excuse me. What I wanted to do is be able to kind of pull that nth power out so I can see what the ratio is, but I can't do that here. So where to begin? Well, what I can do is I can break up the summand into 2 separate sums. One is the sum of 2 to the n over 3 to the n. And the other will be minus sum 0 to infinity of 1 over 3 to the n. So all I did was basically distribute the denominator to the 2 parts in the numerator, and then distribute the sum over that. So we have 2 different infinite series. And lo and behold, both of them are convergent geometric series, because I can see the first one has, it's got a lot darker in here. Oh, crud. Let me see if that looks okay on the screen. Not sure what happened. Bring back the glare a little bit. Sorry, guys. but at least that won't be on this part of the screen. So some other light went out, and I don't know, my first time in this room. So sorry about the glare. Obviously, I won't do this again, at least not in this room. Maybe I can find a better room if you guys like the board. But we're just focusing down here, last problem. So we can rewrite the first one as 2/3 to the nth power. And the second one as 1/3 to the power n. We have the right relationship between the index of our sum and the power. And we can quickly, just by eye, see that the ratio for both of these series is less than 1. So they're both going to be convergent, and we know what they're going to converge to. So this is pretty neat because both of these we have two geometric series in tandem, right? So the first one will converge to 1/1 minus 2/3. And the second one will converge to 1 minus 1, or sorry, 1/1 minus 1/3. What happens? This one, 1 minus 2/3 is 1/3. Flip it over, it becomes a 3. 1 minus 1/3 is 2/3. Flip it over, you get 3/2. And so 3 minus 3/2 is 3/2. Right. So cool little problem, two geometric series. We could split it up. So I guess moral of the story, with a number of these examples that I worked up, almost all of them were geometric series. So obviously, that is one of the ones that you need to be most familiar with. And indeed, as a practicing mathematician, geometric series are some of the most useful because we know what they converge to. So you definitely want to be able to spot a geometric series and figure out what it converges to above all else. But there are a lot of other types of problems that you could be looking at in this section. I'll hopefully have time to do some more examples, but we will have to start in on 9.3 tomorrow. So I apologize for the pacing. It is what it is. This class is intense. So I'm doing everything, like I said, I'm doing everything I can to make it as accessible and achievable as possible, but I'm open to any feedback. If you guys don't like how things are being done in some way or another, we can hopefully find a better solution if you have suggestions, right? But I think that's good enough for today's lecture. Sorry about all the technical difficulties with the lighting and everything. Hopefully it's still a useful video for you. And if I do next Monday, I definitely won't do this room again since it was a bit of a trial. I can at least go back to just writing it on paper and you can have that for reference. But I wanted to give this a go. Maybe I'll be able to find a room with better lighting situations. So we'll see. But all right, guys, have a good day.